See my hackers filling in the room, and yes, there's quite a few of them. Hi, I'm Chris Woodfield with the NANOG Program Committee. So Sunday we had our now regular NANOG Hackathon, and this is the sixth one that we've run over about 3 years, and they keep getting better each time. One thing that I've noticed is that you know, the people that we bring in, we get good crowds, and I think we had about 50 plus people this time, which is really excellent. The fact that we're able to introduce new technologies to people who in many cases have never encountered any specific technology before. Just to back up a bit, we do different themes for each hackathon. We pick a technology or a solution or a specific challenge and then present that to the teams, which then organize on solutions. Many times these are things that, as I said, very few people have seen before. We've gone from host-based BGP daemons to source of truth, config template generators, security, ACL policy automation. This time we did segment routing, which is a new and exciting technology that, yes, a number of people have worked with, but many, many more have not. So the fact that we were able to introduce that to a large group and then within a day have not one, but a large number of different implementations of automated segment routing, update steering, is just amazing to me. The people that come in and participate, they're interested, they're smart, they collaborate well, and they have a lot of fun doing it. And I just want to thank all the participants, and we hope that we see you at the next one. At this point, let me introduce Dip, with Oracle, one of our sponsors, and I also wanted to thank our lab sponsor, Tesudo, who helped us out with the the virtual labs that the teams were working on. So without further ado, here is Dip, and thank you.
Can you guys hear me? I guess, fine. Okay. All right. As Chris mentioned, my name is Deb Singh, and I'm a network engineer at Oracle Cloud. I would start by saying that I'm very proud of Oracle sponsoring this hackathon, as well as organizing it. I would also like to say thanks to the NANOG Program Committee for letting us to do so. And the second thing I want to say is thank you to all my colleagues who helped me in organizing this hackathon. And last but not least, all the hackathoners who decided to show up on Sunday in a weird way to spend time with us rather than, enjoying this beautiful Vancouver. So thank you for that. So a little bit about the hack itself. If you look at the hack itself has three particular domains. One aspect was programming itself, right? You need to code something. The other aspect was around algorithms, to start thinking about algorithmic way of thinking of the network. And the third aspect was the protocols. So if you think about the Venn diagram, we have three domains. It was basically an intersection of all the three domains. We had around 50 plus hackathoners, which was a good attendance for a hackathon. This was the first time we had a remote participation, which is also a big first step for the hackathon program itself. And the hack, we started around like 10:30. Every team, once the team was given the hacks, they started working from 10:30 to 6 p.m. Sorry. And as you can see, it's a long day. A little bit about the hack itself, more into this. So the hack was divided into three sub-problems. Problem number one was that you have been given a network, and what you have to do is you need to extract the topology information, create a network model, represent all the things which you need to solve your second problem. Basically, you need to extract all the information so that your model represents the right attributes which you need to solve for the second and the third problem itself. And the second part of the problem was once you have created this network model, what you have to do is that you have been given certain TE constraints, and the ask was basically, okay, go and solve these TE constraints. For example, could be between point A and point B, could you figure out two disjoint paths, right? Or could between point A and point B have been given certain constraint, like you need to have this amount of bandwidth available, otherwise the path itself is not valid. So those were some examples of the TE constraints. And the last but not least, once you have computed the path, what you have to do is go ahead and program the network itself so that that path exists. Before we really delve into the hack itself, like the team started working around like 10:30, but before that, an hour, we tried to spend some time into covering the background which we needed to cover the hack itself. So like for instance, we started with the problem, then we spent some time with some of the graph theory which you need to have so that you can solve these problems. Then we covered some aspects of the network flow theory. I tried to show some of the linear programming aspects as well, and then covered some of the protocol tidbits for like BGP and segment routing, which you need to cover the hack. So that was the first hour of tutorial, which we covered. Then the next slide. Okay. We had around 9 teams. After we had around total 9 teams, and each of the team itself has around like 5 or 6 participants in that. So it was around, as you can see, it comes around like 50. These are the pictures from some of the teams, various teams, which I just showed it to you. Once the tutorial itself was done and the team started really working on it, what I noticed was there were some really good questions and which people were asking. And one thing I would say that in the amount of the problems which I presented, one of the problem itself was a multi-commodity network flow problem, and I was thinking it may be too much, or maybe for the hack itself, maybe I should take it out, but eventually I decided to have it there. And the people at around like 3 or 4 o'clock, they were saying, oh, we are done with the rest of the task. Tell me how can I solve this multi-commodity network flow problem slow. I was like, oh, that's really good. I was amazed with that. It was overall generally a good experience for all of us. We had different background of people in the hack. Some people had actually very strong development background. Some people have no development background at all, but they all actually learned a lot from the hack itself. So, and one of my goal itself here was not necessarily to go and like win the hack itself, but was to create enough interest that once the hackathon itself is over, you go back and start looking at the problem, how do I really solve that, right? And that's to me is a real win for the hackathon itself, that the people go back and have really interest and then spend some more time to understand the subject itself. Once all the teams finished their hack, every team was given an opportunity to present their hack. So it was like 2 or 3 minutes. Everyone, spend the time. So how they approached this problem, and what we did was afterwards there was a voting done for each of the hacks, and these are the top 3 teams who won the, these are the top 3 teams who were voted the highest. And with that said, I would like to invite Cat 5e Hurricane on the stage.
Hi, we are Cat 5e Hurricane. My name is Ben Anderson. This is Tom Sutliff and Soham Shah. So our product overview took into account a couple technologies that actually weren't in the description of the hackathon. So we used Napalm as the driver to interact with these devices. What that does is it abstracts away the actual transport layer and interacting with devices, returning a common data set between various platforms. We also use NetworkX, just like many other teams, to do the path calculations. The only difference there was that we actually dynamically supplied weight-based information to NetworkX. We also used BGP LU for southbound SR via ExaBGP, and then our controller, which was kind of took into account a couple of these technologies, and that's what we produced. So this is the sample topology for anybody that was curious. So we were primarily interacting with VMX3, and that's what we would program with our controller. And so we did take a little bit of a different approach. Rather than just solving the 3 or 4 problem sets that were presented in the tutorial, we actually decided that we wanted to take an external approach, observing this network and taking into account things that traditional routing protocols wouldn't necessarily observe. We did this in kind of a generic manner, just for the sake of the hackathon, based on like just traffic that was going over the network. So this ensured that as traffic or situations change within the network, that we could dynamically update, provide a custom weight value to network X, and then get the new path from that. So this is kind of how we laid out our software. The test script just continually ran and got input from the path computation algorithm, which then output to our route logger file, which exabgp used to send an update to VMX3. It is, you can kind of see it there at the bottom. That's kind of like what the final statement looked like after we ran the computation. So Tom is going to talk a little bit more about the Network X aspect of the project.
Yeah, great, thanks, Ben. So as Ben mentioned, we use Network X to basically create our network graphs, to take a look at what the initial view of the network looked like, and then also to recalculate our best path anytime that we observed a change in the network. So on the left here, you see the initial code. That's all it takes, just a few lines of code to actually input the weights and the links, the edges, the nodes, all of that that's required to build and draw the network. And then also just to actually draw the graph on the right. So using matplotlib, you can just, with just those lines, you can create it. It's pretty easy. Here we go. So this controller basically shows that for the controllers pulling the network on a regular basis. So on the right, we see the controller pulling the network, taking a look at interface stats and different things that can be used as a decision point to determine if there needs to be a change made in the network. So anytime that's done, the controller will make that decision and decide that yes, there is a new best path, and will actually generate the commands to actually push to exabgp, which will then actually push to the network. Here we see some output from the exabgp controller. The script is run, it's initialized. We see that basically the purpose here is to connect to the controller. So then we have commands there in the box, the selected box. We have the commands that exabgp will push to the network as a result of the change in the network. So at the bottom there, we see the BGP adjacency that's formed between the controller and exabgp. Initially, this is the network as we started. Ben mentioned here we have, the topology that everybody used. The initial best path is from VMX3 to 1 to 4, with the destination being the 10004 at the bottom there, on the bottom left. And here we go. So we run the Python script to take a look at the network based on the network graph. And then we see here the best path at the end is saying 314, as I mentioned before. This is the initial look at it before the controller has noticed any change in the network. Here we have the MPLS label that we're imposing, which is the 800,004 label there. Okay, so then now we see that the path between MX3 and MX1 has taken additional traffic. And this really could be any observable change in the network, but at this point we just decided to use some traffic flow. But once that's happened, now we need to take a look and see, once the controller determines that there's a change, what change needs to be made, and Soham is going to talk about that now.
Thanks, Tom. So now that we have a particular change in the network and the state of the topology has changed, what we ideally want is a better optimized path to go through VMX3, VMX2, 1 and 4, or VMX3 to 5, 4, whichever is better in terms of link bandwidth. So we go back to Network X and the computation engine to determine this path, taking into account all the parameters which we have extracted from the particular model given. So this is the second run, what we call when the controller detects that there is a change in state. What we essentially do is we go back to Network X. We saw that, okay, yeah, MX3214 could be a better path than what it is going through currently. So in order to do that, what we rely on is the delayed IGP cost to calculate metrics until node 1, and then push MPLS labels through segment routing and BGP LU So we have 800,001 and 800,004, which are nothing but MPLS pops, a popping operation done at 1 1 and before 4, which is the destination. So this is just a detailed deep dive at the head end, which is MX3, which is a source. So when we do a show route 10.004, which is the destination, we see that couple of labels have been pushed, and we are relying on IGP to go till the first label, the first pop operation takes place. This is a trace route from the source till the destination and the labels which are being pushed. So again, this is if we want a disjoint path kind of a scenario wherein we don't want a particular path being used already due to a flow transition, this is what we could have done as well. So this was the third run, and we see that final advertisement from the route logger file, which is, choose your next best hop and then change the label so that the swap operation takes place at a different node than what it was used previously. So coming to the most interesting part, gathering data was a big task because the data formats were a bit difficult to deal with. Secondly, graph theory was really interesting, and integrating graph theory with the data set which we had was a fun task, and along with the computation algorithm. So that is something which we learned a lot, and we had a great time with it. And finally, we learned how to programmatically push SR tunnels through BGP LU. To conclude, we would like to believe that this could be a good approach to try out in your MPLS cloud. It may benefit you. And harnessing all of these technologies, which we already have in our network, whether it's BGP, segment routing, or just some overhead in terms of a controller to poll your various network devices. And we take care of link failure or any reservation bandwidth or any such scenarios in the end. So with that, we would like to thank every one of you and all my teammates. Thanks.
Thank you, Cat 5e Hurricane. Congratulations. And I'd like to invite our first runner-up team, the Buffs, up to the stage to present their hack. Thank you.
Hi, thank you for having us here today. We're Team Buffs, and we're graduate students at University of Colorado Boulder. So this was our journey as we tried to implement segment routing in one day within 6 hours, where we had to learn a lot of things. The idea was to automate traffic engineering in a dynamic way during real time. So once we had the hackathon problem set, we broke it down into achievable elements that we each took up, and then together we would finally integrate it into one working solution that we could run. The first step was to gather the topology information in the network in a dynamic fashion, and then it was to use the topology information to model a graph. We had to work on CSPF, because SPF alone would not achieve the requirements that were given to us. So we had to modify it for each of the problem statement, each of the different scenario, take into consideration the different constraints, whether it was disjoint path, whether it was the bandwidth subscription. So modify the algorithm to consider that, and then find the best path. And then the final 2 steps were to use once we had the best path, we had to dynamically configure the routes with the MPLS labels, and it was finally to push it to the network and validate and see if traffic is taking the path we meant it to take. So these were the steps. There's a visual representation of what we were trying to achieve. On the top left, we were gathering information, the topology information. We were working with Juniper devices, so we use Juniper's inbuilt library PyEZ. It makes remote procedure calls on all the boxes in the network, gets the information, topology information in JSON format. Then we pass through the JSON format to obtain a data structure, which is basically the LSA, along with some of the traffic engineering elements that the CSPF algorithm can use to make decisions. And the second step is in the top right, where we use the CSPF algorithm. We had 3 different scenarios, and we wrote 3 different functions wherein, based on the requirements, we run SPF, taking into consideration the constraints defined, and come up with paths that will work for each different scenario. Then we use then we use segment routing paths. We construct the routes based on the labels. We dynamically assign the labels to And once we have the routes ready, we push it into the network using XRBGP as an interface. It establishes a BGP session with the MX routers in our network, and then we push the BGP LU routes into our network. So regardless of what the forwarding table was before we did this, once we push these BGP LU routes, the route manipulation will take effect, and the paths taken will be the ones we want it to take. So we're trying to do that in real time. So with topology discovery, as I mentioned, we use the PyEZ library, and this is what the data structure looks like. So for a given link, we have this information where it talks about the source in that link and the destination within that link itself. And it has traffic engineering metrics like cost, which in this case is 10, and 100 Mbps, which is the reservable bandwidth for that link. So we get this information, we parse it, and then that would be given to the CSPF functional block. So this was the topology information we discovered. While parsing it, we found 3 additional links than the topology that was given to us. But not to worry, the shortest path algorithm that we wrote works for any topology, so it was able to accommodate that as well. So we had 3 different scenarios. We'll go through all different scenarios and how we had to modify the SPF to accommodate for that scenario. The first scenario was straightforward, where we had to find the shortest path between MX3 to MX5. We just ran the SPF, and we were able to find the shortest path, which is as indicated, as highlighted in the diagram. In the second case, it was more challenging. We had to find as many disjoint paths as we can in the network. In this case, it was between MX1 and MX5. So the first step is still the same. You run SPF to find the shortest path between MX1 and MX5, and then you remove the links that were used, and you update the topology table, and then you run shortest path again, and you iterate over it to find disjoint paths. So once you remove the black path, which was the best path, you get suboptimal routes next, which are all disjoint, which are the blue paths and the red paths indicated in the diagram. So this is how you have to modify the SPF to accommodate for the second scenario that we were required to accomplish. Now, the third and final scenario, here the goal was to make sure that all of the link bandwidth is utilized. So here, again, we don't worry about the disjoint paths. The goal is that if user 1 is using an amount of bandwidth, so now so even though the topology information said the available bandwidth is 100 Mbps, if user 1 is already using 50 Mbps, you have to take into account what is currently available. So again, you need to subtract that from the pool of available bandwidth and then run the SPF. So that was the idea. So as multiple users use that, you keep giving them paths until all paths are possible. So that was the third scenario. And XRBGP is an interface. So the output from the CSPF algorithm, it gives us the path. As you can see, it says MX3, MX2, MX5. That's still not the configuration. That's still not the route. We just have the path. So we have to use the code again to find the information. It has to go into MX2, find what is the IP between MX3 and MX2. And that's how the neighbor command looks like. You have an IP reference, you announce the route. So again, the code builds this during runtime dynamically without any intervention. So once the route is built, XRBGP is the interface for us. It establishes a BGP session with the VMX router, and it announces this route, and it goes sits in the forwarding table. And once that's done, this is how the routes will look like. You can go into all the network. So these are the routes we saw on the VMX routers once the routes were pushed. As you can see a label reference. And for a given label, you see the exit interface and the destination for a particular destination IP. So if you're trying to reach from MX3 to MX5, it will take the labeled paths, and it'll take the path that we've manipulated it to take. So we are controlling the network using code. So these are the expected results. These were the labeled paths that we wanted it to take. Here are the screenshots proving that. So in summary, we learned a lot of things. We've been doing SDN since 2 months in our college, so this is a new thing for us. So there's a lot of things to learn about. There were many ways to parse the topology information as well. There was CLI, there was different tools that you could use. We went with the Juniper API because it's dynamic, it's reliable. So even if when you're parsing the data, you don't find any data, your code is not going to break. Your code is still going to work with whatever is available, and it parses that data. So that's why, even though we didn't know the API, that was the right way to do it. So that we tried to learn that, figure it out, and then go about with that. And with the CSPF as well, for different scenarios, we had to write different functions to modify SPF so that that would fit the requirement that they expected us to achieve. So it was fun playing around with the SPF, which we knew, and tweak it a little bit. And with ExaBGP, we had a lot of issues installing it. The installation was not clean on using Python 3. So, and then with some help, we figured out that you didn't have to install the full features. You only needed a bunch of features to make these things work. So once we were able to work around that, we were able to solve the issue, use this as a tool, and kind of bring everything together. So it was fun. It was amazing to work with some of the best minds in the industry, be in the same room as them, interact with them, learn, and to build an end-to-end solution within a matter of 6.5 hours to kind of visualize what would happen and bring them all together was exciting. And it was an amazing experience. This is the first time we were working as a team as well. So to work together, to be in sync and build that rapport was a really good experience to have. And a lot of credit to all our team members. We worked at this together, and a lot of credit to Professor Jose Santos as well, who was here with us, and he was our guide through this as we worked on it. And special thanks to all the organizers. I think they did an amazing job putting together this event and have remote participants as well. That was great. And thanks to all of you for your attention. This is the contact details. If you have any questions, we're happy to answer. You can get in touch with us as well. Thank you.
Thank you, Bus. Before we go off stage, can I, a quick second, I want to go back and their title logo, which I got a lot of the cafe. Did I hit the wrong button? There we go. I'm going to go back for a second because I thought that logo was just awesome. That one. The hurricane with the bundle, I thought that was really great. But they went that really quickly, so I just wanted to pull that out. Okay. Now we'll have Lost Pod come on stage. I'll get you back to where you were. Thank you.
Oh. How far are we out? Okay. Hi, I'm Clinton with the Lost Pod team. Also on our team, we had Cesar, Adrian, TJ, and Joshua on our team. So our approach for this hackathon to break down the problem and attack it, we use the NCC client with netconf to grab the topology, information from the MX1 router from the TED database, and then parse the return XML into a Python data structure where we grab the attributes and items that we needed. Then we pass the captured data through the Network X graphing library to create a undirected graph and a digraph for a directed graph to store the topology information, and then use the algorithms that come with Network X to compute the shortest path through the network topology. Then we created separate functions to solve each of the 4 problems that we were given, and we passed the graph data that we collected from the network to each of those solver functions to solve the 4 problems. Finally, we take the output solved list of the computed path, and we reiterate through the graph structure to pull out the loopback addresses and the segment labels to generate the BGP LU routes. And then we use the ExaBGP BGP daemon to the MX3 router to advertise our BGP label stacks to install them in the network. So this is just a view of the default state of the network. So it shows we're on MX3 and we're looking at the loopback address for MX4. There's no labels installed, and the trace route is just kind of IP routed from MX3 to MX1 to MX4. Problem 1 is we just needed to compute the shortest path from MX1 to MX4. So you can see in the left-hand side here, right-hand side, we have the parsed out information that we got from the NCC client with the router loopback address and the router segment label, and then we have the list of links on each of the MX routers with their IGP costs, their bandwidth capacity on the link, and then the link segment label that if we needed to use it. So the solution to this problem was pretty straightforward. You just run the SPF algorithm and it returns at the bottom there. The shortest path is from MX3, MX1, MX4. And then we write that out to a log file that the exit BGP reads and it installs the route. So this just shows here on MX3 that we now have a labeled route to get to MX4, and you can see the label as well in the trace route. Problem 2 was we needed to compute a shortest path from MX3 to MX4, but you had to have 200 megs of bandwidth. And so our solution to this is we loaded up the graph, we removed all the edges that had less than 200 megs of bandwidth, and then we just computed a shortest path on the remaining links. And at the bottom there, the only path that you could choose or get as a result was MX3 to 2 over to 1 and then down to 4. And again, we installed that, and you can now see that we have 2 segment labels in the show route command, and the trace route also shows the labels from MX3 to MX4. The third problem was a little more challenging. You had to compute 2 paths this time. Path 1 needed 200 megs of bandwidth, and path 2 needed 60 megs of bandwidth. So the first path was from MX3 to 4. The second path was from MX5 to 4. So our solution to this is we created a directional graph this time, and we computed the path 1 using that directional graph, and then we removed the path 1 bandwidth, the 200 megs, from all the directional links that it used. And then we went and computed the shortest path for path 2, but we removed all the edges that didn't have 60 megs of bandwidth available, and we ended up with this result where path 1 went the previous route. Path 2 kind of has to go on a milk run. The only bandwidth left available, you have to go from 5 to 2 to 3 to 1 and then back down to 4. We also did a second solution one of our team members did where we actually split the path bandwidth. So the first path you wanted 200 megs. On the shortest path you could only get 100. So we provisioned that and subtracted the bandwidth, and then went and computed the next available path that could support the remaining bandwidth. And so for path, we got like 2 paths to support the 200 megs of bandwidth, and then we repeated the same thing for the second path, and we end up splitting it 50 megs on one way and 10 megs on another. Problem 4 was you had to compute 2 disjoint paths to the network, and so we used a very simple algorithm for this. We computed the shortest path from 3 to 4, and we removed all those edges, and then we computed another shortest path, and we got 2 disjoint paths from one went down one side and the other path went down the other side. Our learnings from the hack. The initial problem, I think, was pretty daunting when we started in the morning, but we kind of broke it into 3 sections, and that really helped. We had one person work on data collection, a couple of people work on solving the problems, and then a third person was working on the exit BGP. And by breaking the problem apart, that really helped. I found it was a great way to network with other professionals and learn something new. It also got practical experience with the Python NCC client, which we hadn't played with before, Network X module, which is really great, and the exit BGP for announcing the BGP-LU label stack information. One of the problems I had initially was trying to get the NCC client RPC call to show the detail output, and I guess on Juniper, if the display XML RPC command is your friend, because it'll show you the exact call that you need to make in the options. That once I found that, it really helped me out. Just a comment about the Network X module. It has a lot of pre-built algorithms and data structures that are really useful for this kind of network modeling. And TJ had a problem the disjoint path, where we could only get one of the paths installed originally, and it's because we forgot to, or we didn't set a path identifier on the two routes, so it kept switching it back and forth rather than installing both. And once we put path identifiers, both routes got installed. And finally, I'd just say I think it was a great event, and I would encourage other people to join one of the hackathons in the future. So we all really enjoyed it. Thank you.
Thank you, Lost Pod team. Thanks again to all of our hackathon participants. The next one will be at the next NANOG, and we hope to see you there. Thank you.